Hey everyone, welcome to the channel. Have you ever wondered how Instagram handles millions of likes per second or how Netflix streams to millions without lag? Today, we are going to break down exactly how scalable systems are designed, step by step from a single server to a global architecture that can handle millions of users. And by the end of this video, you will not only understand the architecture, you will think like a real system designer. Let's dive in. Oh, and if you love content like this, hit that subscribe because we will design a new system every week. So, what exactly is scalability? Simply put, is the system's ability to handle more load by adding more resources. Imagine running a cafe. At first, you can serve 10 customers. As more people come in, you hire more baristas instead of just buying a bigger coffee machine. That's horizontal scaling. Vertical scaling, on the other hand, is just upgrading your coffee machine. Faster, but with limits. In system design, we mostly scale horizontally, adding more servers instead of making one supercomputer. Now, let's say the big picture. A scalable system logically has it has these basic building blocks. Client layer. Web or mobile app sending request. CDN. Delivers static content close to the user. Now, let's say the big picture. A scalable system typically has these building blocks. Client layer. Web or mobile app sending requests. CDN. Delivers static content close to the user. Load balancer distributes incoming traffic. Application servers, the logic layer, usually structured microservices. Cache layer, fast memory to reduce database heats. Database layer, where all the data lives. Message queues, to handle async jobs and spikes. Monitoring and logging, because what you can't measure, you can't scale. Don't worry, if this looks complex, we will zoom into each piece. Now let's discuss core components. First, let's start with load balancer. Imagine millions of users hitting your app at once. You don't want one server to die of exhaustion. That's where the load balancer comes in. It splits traffic evenly across servers using algorithms like round-robin or list connections. A load balancer works at the network or transport layer. It doesn't care if it's a login request or a checkout request. It just spreads the load. A load balancer can work at layer 4, that's the transport layer, where it just looks at IP addresses and ports. It's like, oh, you're going to port 443? Cool, let me find a server for that. But it can also work at layer 7, the application layer, where it gets a little smarter. At this level, it can actually pick into HTTP requests, check the URL path, and make decisions based on that, kinda like, oh, you're trying to hit /checkout? Let me route that somewhere special. Now let's talk about caching. Think of it as your system's short-term memory. Instead of fetching the same data over and over from the database, we store it temporarily in Redis, Memcached, or even a CDN. Results: fast reads and happy users. Common caching strategies include write-through. Cache updates instantly with the database. Write around. Write skips the cache and updates on reads. Write behind. Cache writes first, database updates later. TTL. Data expires after a set time. Event-driven invalidation. Cache clear when specific changes occur. Now, Redis. It isn't just a cache. It's an in-memory data store that supports list, sets, sorted sets, persistence, and even pops-up messaging. Memcached is simple. Super fast key-value caching for things like sessions or HTML snippets, but no persistence or context data types. And finally, a CDN. A global caching layer for static content like images or CSS, served from servers closest to the user. So, if your site is hosted in the US and someone in Australia loads it, CDN makes it feel local, faster and smoother. Caches themselves need to scale too. We can shard Redis clusters or use replication to handle higher read loads and improve availability. Now databases. Databases don't like getting overloaded. That's why we use different strategies to scale them. We usually choose between SQL and NoSQL databases based on the data type. For example, SQL is great for structured transitional data while NoSQL works better for unstructured or high-volume data. When it comes to scaling, we use replication to improve availability and fault tolerance, and sharding to split cache dataset into smaller, faster chunks, like storing uses A to M in one shard and N to Z in another. But that can create hotspot problems. For example, if all traffic hits one shard because of a trending celebrity, to fix this, we use consistent hashing or other smarter sharding keys to spread load evenly across shards. Now let's look into asynchronous processing. Not every task needs to happen right away. When a user uploads a photo, the main job is to save it fast. But other tasks like generating thumbnails, compressing images, or sending notification can run in the background. That's where asynchronous processing comes in. Instead of doing everything in real time, the app sends the background jobs to a queue. Using tools like AWS, SQS, Kafka, or RabbitMQ, workers then pick up these jobs and process them separately. This approach keeps your main app snappy, scalable, and resilient. Because a sudden spike in uploads won't slow down the user experience. This approach keeps your main app snappy, scalable, and resilient. Because a sudden spike in uploads won't slow down the user experience. You can even use retry mechanisms and dilator queues to handle failed jobs safely. Now let's look into microservices. Each microservice is designed to handle one specific job, like authentication, payments, or notification, and it gives no user state. That means the service doesn't store session data or use user info locally. Instead, all stateful data lives in a shared store like a database, Redis, or session manager. Because the services are stateless, we can easily spin up or shut down instances whenever traffic changes, perfect for autoscaling in the cloud. Think of it like Lego blocks. Each piece does one job, and you can add more blocks anytime without breaking the others. This makes the system scalable, resilient, and easy to deploy, since any instance can handle any request independently. Now let's look into storage monitoring. When it comes to storing large files like images, videos, or backups, we don't put them in databases. Databases are great for structured data, not for massive binary files. Instead, we use object storage like Amazon S3, Azure Blob Storage, or Google Cloud Storage. These are built to handle huge volumes, provide high durability, and let you access files from anywhere, often through URLs or APIs. But storage is just one part. We also need to monitor everything. We check latency, error rates, throughput, and uptime using tools like Grafana or Datadog. This helps us catch issues early, like slow uploads, failed API calls, or storage cost spikes, and keep systems reliable and efficient. Now let's make this real. Imagine we are building a social media app. When a user posts something, the request hits the API servers. Metadata and content go to the database or object storage. A system or message is pushed into a queue for the feed service. Other user feeds are updated asynchronously and cached. When someone opens the app, the feed is served from cache super fast. This separation of write path and read path keeps the system scalable. Scaling sounds easy, just add more servers, right? But in reality, it comes with some serious challenges. First, database bottlenecks. As traffic grows, your database can quickly become the slowest part of the system. Slow queries, inefficient indexes, or write logs can bring everything to a crawl. That's why we use techniques like read replicas, caching, and sharding to spread the load. Second, consistency issues. In distributed systems, not every node has the same data instantly. We often rely on eventual consistency, where data syncs over time, but that can lead to temporary mismatches users might notice. Third, network latency. When your app runs across multiple data centers or regions, network delays can add up. Using CDNs, edge caching, or region-aware routing helps reduce these lags. Fourth, cost trade-offs. Scaling always costs more, whether it's compute, storage, or bandwidth. Smart teams monitor usage closely and scale efficiently, using auto-scaling, serverless options, or spot instance where possible. In the end, scaling is all about balance, finding the sweet spot between performance, reliability, and cost. That's what separates a good system from a great one. Let's wrap up with some best practices every scalable system has in common. First, design for failure. In live systems, things will break. Servers crash, networks drop, and APIs time out. So all this designed with redundancy and graceful recovery in mind. Second, automate scaling. Use auto-scaling groups or serverless architectures to automatically add or remove resources based on demand. That way, you handle traffic spikes without manual intervention. Third, go stateless. Keep your services stateless so any instance can handle any request. This makes horizontal scaling, adding more instances, super simple. Fourth, continuous monitoring. Use tools like Grafana or Datadog to track metrics like latency, error rates, and resource usage. You can't fix what you don't measure. And finally, start small, iterate, and scale with demand. Don't over-engineer from day one. Build something that works, monitor it, and grow as your users grow. Because in the end, scalability isn't just about adding more servers, it's about designing smarter, more resilient systems that grow effortlessly with your business. If this helped you understand how app scales to millions, drop a like in the comment and tell me what system you would like me to design next, maybe Netflix, Uber, or Twitter. Don't forget to like, subscribe, and share. It really helps the channel grow. Until next time, keep building scalable systems.